So we're told that this chain of restaurants has been required to display some calories, and the average calorie intake of dinners at the restaurant is 1,100 calories. Nutritionist decides maybe there's been some significant decrease since this last kind of poll or last averaging, so it might be less than 1,100 calories. So again, we're talking about averages. So over on the left side, we do want to have something that shows us average. But remember, we do want to deal with our population parameters. So immediately we can rule out A and D. Our hypothesis should never include anything to do with these point estimates of X bar. So it's going to be B or C automatically. Mu equals 1100, mu equals 1100. And then we have to decide which one is appropriate. Well, we can see that we do have, is there a significant decrease? So we do want to check to see if it is a significant decrease. So we would be looking at C here. So C would be the correct answer for this particular one. Alright, we've got this claim that they can save us $432 on average. And we're not so satisfied. We don't think that it's quite 432. We think that maybe it's a little bit less. So we did our own test. We did a poll of 82 people, and what we found is they saved an average of $395, and with a standard deviation of 102. So we're asked to test this claim at 95% to see if this is an overstatement, and then define the p-value. First things first, let's go ahead and set up our hypothesis. We've got our HO, we've got our HA. We're talking about the mean, so this time we look at the population parameter for the mean. It's going to be equals, and then we'll have to see. So it could be equal to this 432 that they're claiming. It has nothing to do with the test, again, has nothing to do with this test sample that we had done. It has nothing to do with the sample, just what they were claiming. So it could be equal to 432. Or we want to test that this is an overstatement, that it's actually less than this. We'd like to test that it's actually less than that. So this would be our hypothesis. From there, we do have to go ahead and find our test statistic. So again, our test statistic is this Z equals our X bar minus our null, all divided by the standard error of our X bar. So in this case, what we get, we have X bar is 395 minus our null value, which is 432, all divided by the standard error of X bar, which again is just the sigma divided by the square root of n. So continuing on, just plugging these things in, we saw that 395 minus 432, all divided by, your standard deviation was 102, and we had a total of 82 of these. So this will be over the square root of 82. So continuing on, let's see what this gives us. It gives us 395 minus 432, negative 37, all divided by 102 divided by the square root of 82 is 11.264. And if you put these two things together, we finally see that our test statistic is Z equals negative 3.24. So we're going to go ahead and round this to the nearest hundredth again, because we do need to see, well, first of all, that we're looking in our table for this, and it only shows places up to the nearest hundredth. Okay, so now they're asking us find the p-value for this thing. This is our standard normal curve. So we've got 1, 2, 3 about, and negative 1, negative 2, negative 3. So it's far out here. And what they're asking us to do, the p-value, if you look back at our hypothesis, we were asked to find the p-value, the probability that this thing is actually less than this. So this is a one-tailed test because we do not have the not equal. That would be two-sided. So it's just one-tailed. And furthermore, it's a left-tailed. So we're looking for this area over here, just to the left of this. It should be very, very small. Let's go ahead and look it up. If I look in the book, I get negative 3.201234. Looks like it's going to be my p-value. It's going to be 0.0006, and that's our answer. Okay, so we've just done our p-value, found our p-value is really small, it's 0.0006. So, because we were testing this at 95% confidence interval here, or I'm sorry, at 95% confidence, our alpha significance is 0.05. So, as it turns out, yes, 0.006 is much, much lower than 0.05. So because our p-value is small in comparison to our confidence level, this tells us we do have to reject our HO. So we can see immediately it's going to be either B or C, reject the null hypothesis. And so what does that mean? Recall in the last problem we had our null hypothesis was that it was equal to this 432. Well, because we've rejected that, the only alternative is that the alternative hypothesis, yes, that is actually less than 432. So we can see that, yes, we can conclude that the advertisement is an overstatement or overestimate. Absolutely, it's going to be that one. Over here we have not enough evidence to conclude. No, it's going to be B here. For this particular problem, we want the sample size here. So we're given that, or we're going to go ahead and assume that the population standard deviation is 102. This is given to us by a prior study. We want our margin of error to be at most $10. So we want our margin of error to be $10. And we do want this at a 95% confidence. So recall that the formula is just written here. This n equals z star times the standard deviation divided by the margin of error, and all this whole thing squared. So before we start, we've got almost everything. We've got the standard deviation, we've got the margin of error written up here. This z star comes from this 95% confidence level. And furthermore, I guess it should actually be alpha over 2. Let me squeeze that in there. Z star of alpha over 2. So, remember, this is one of those ones that you may have remembered. Your alpha here is 0.5, if you don't remember. And you divide that thing in half. So, your alpha here is 0.05. You divide that in half, you get 0.025. You could look into your table to find out what that is. It ends up being 1.96, if you recall. So our z star of alpha over 2 for 95% is 1.96. Standard deviation is 102. We'll plug that in. And the margin of error is $10. We'll plug that in. The whole thing is squared. So when you do go ahead and punch this in, you should get 19.992, and we're asked to square that, which ultimately gives us 399.68. Of course, we want the nearest whole number, so the smallest number of people we need to poll. Well, you can't poll a fraction of a person, so this would be ultimately incorrect if you put this in as is. Remember, we always round up. It doesn't matter, it has nothing to do with this 6. It's going to round up to 400. If it was 399.18, it would still be 400. So just remember, when we're talking about sample size, we always round up. It has nothing to do with this 6 at all. It's just the fact that there is a fraction, there is a decimal after it, so it's going to be the next largest, or I guess the next whole number. So we'd have 400 for this sample. We want the probability of the standard normal less than 1.24. If you think about this, as far as drawing this thing out, this is our standard normal curve. We've got something right here. We want the probability that it's less than this, so we're indeed talking about this area. So this is fine just to go ahead and find 1.24 in the back of your book under standard normal curves. It's going to be on the right page, so page 363. And when you do look it up, 1.24, should come up with 0.8925. 0.8925. So we just wanted to see, can you use your chart? This one is very similar to the first one. If I drew this out, standard normal curve here, 1, 2, 3, -1, -2, -3. Somewhere around here, we want the probability that's actually greater in this thing, so we're indeed talking about this area. Now there's two ways to go about this. You could go ahead and look up this value. In your chart, it's going to give you what? It's going to give you a different value than that. If you look it up in your book, -2.12, it's going to give you this value right here, which is not what we want. We want the black area. So if you do look that up, there's two ways to do this. Let's do it that way. You find it should be 0.017. So you would look up, you would see that this is 0.017. And the way to get this black area would be to do, well, the whole area is 1. So we do 1 minus 0.017, and we come up with, what is this? I guess 83, so 0.983. Oh, that's right. So you should come up with something like this for your area. So that would be the probability. The other idea is, well, again, you could just switch the sign and find positive 2.12 in here. And if you look up positive 2.12, it's exactly 0.9830. So either way, you should come up with the same answer. I know we talked about both ways. It's whatever way works for you. We want the probability that a single student scores less than 1,300. And we're told that each person's scores is normally distributed with a mean of 1,200, standard deviation of 200. So before we can do this, we can't use the standard normal curve just yet. We have to find the z-score of this thing. So again, remember the z-score would just be what we observed minus the mean all over the standard deviation. So in this case, our z value is going to be, what we're interested in is 1,300 minus the mean is 1,200, all divided by 200. And remember, when we talked about x bar, if this was x bar, the standard deviation was the standard deviation to x bar, so that changed. But here it's a single person, so it's just as simple as using this standard deviation given to us. So once you do this, you get 100 on the top. 100 divided by 200 is going to give you 0.5. So our z is 0.5. So rather than do probability of x less than 1,300, it's going to be the same thing, equal to the probability that z is less than 0.5. That is, standard normal random variable is going to be less than 0.5. And this we can look up in our chart. This is the nice one where we have less than. It's going to be this kind of area here. This is 0, this is maybe 0.5. We're talking about less than. So you just look in your book, find on the right side 0.5, and we're interested in 0.50. So 0.6915. So this is 0.6915, and that's the probability. Again, we just want one single person greater than 1700. We'll do it the same way. First of all, we have to find the z-score. So it is what we observe or what we're interested in. And we're going to go ahead and subtract off the mean and divide by the standard deviation. Alright, so here I think I gave you a general one, the observed minus the point estimate, or I'm sorry, the population parameter divided by the standard deviation of the population parameter. That works too. So we observed 1700. We're going to subtract off 1200, that is the mean. And still using 200 as our standard deviation. So once you go through all this, you do get 500 on the top and 200 on the bottom. And you do 500 divided by 200 to get 2.5. And so our probability, rather than the probability of x is greater than 1700, is going to be probability that our standard normal random variable is greater than 2.5. Again, the direction stays the same. The only thing that changes is x becomes z and 1700 becomes 2.5. We use the z-score there. So if I were to draw this out, we'd have the 0 and we'd have 1, 2. Be a little bit out here. We're interested in greater than this thing, so this area above it. So this is kind of like question number 2. You have two options on doing this. You could look up in your book positive 2.5. It'll give you this red area, which we're not interested in, and then subtract it off. That would be the option number 1. So if we do 2.5, it's going to give us 0.9938. So this is 0.9938. And of course, to get our actual probability, we would have to do 1 minus 0.9938. And we'd come up with 0.0062. The other option is, well, you could just look up the opposite sign. You could look up negative 2.5, and when you look up negative 2.5, you come up with the same thing, 0.0062. Again, the reason for this is because it's symmetric. Yeah, I could find that, or it's just easy enough to go ahead and say, well, if that's whatever 2.5, if I find negative 2.5 over here, these black areas are the same. So that's what I'm doing when I'm just changing the sign. So either way, there's two methods to get it. Make sure you know one of them. We've got a surgeon. Not a very good surgeon. Probability of success is only 6.25%. Or we could call this 0.0625. We could change it to a decimal. And they're asking probability of the first success on the 4th patient. So we have to think, okay, clearly this is not equally likely, right? We're interested in the 4th patient, right? Each trial, however, has the same success, and it could be a success or a failure. That means each trial, each patient is the trial here. Each patient is a Bernoulli trial. It could be a success, could be a failure. And they all have either 6.25% of success or 93.75% of failure. So looking at this, we can see it's either going to be geometric or it's going to be binomial. We just have to decide exactly which one it is. Remember, binomial has a fixed number in here, and we're asked to find the total number of successes, whereas the geometric is this one where on the last trial we get a success. So when we take that into account, the probability of the first success on the 4th patient, this tells us it is going to be geometric. So let's go ahead and label everything. We do have our P. Our P is 0.6, I'm sorry, 0.0625, which means our Q is 1 minus 0.0625, so it's going to be 0.9375. And let's see, what is our N? Our N is 4. And so the probability that on the 4th patient we get the first success, if you recall, it's just going to be this. I'm sorry, write this in the right order. Q to the 4 minus 1, usually we have N here, times P, which makes sense. You just have to get 3 failures first before you get the first success. So that's the geometric there. We just have to go ahead and plug everything in. So the Q is 0.9375. We want to cube that, and then multiply it by 0.0625. And this will be the probability that we're looking for. The 4th patient is the first success. 0.9375. When we cube it, which means multiply by itself 3 times, we'll get 0.82 4. Let's go with that. And over here times 0.0625. Once we multiply that out, we do get 0.051. Let's round it to 5. That's fine. And so we're asking you to go ahead and leave this as a decimal, not to convert this to 5.15%. But that's the idea there. So a continuation of this surgeon problem, we have a couple of them, is we're asked how many do we expect, how many patients to go through until we have this first successful surgery. We just found the probability that the 4th patient is a success, or the first success. We can do this for a lot of them, but we want to know the expected value. So again, we're talking about until the first patient is the first success, so this is still geometric, because we're still looking for the first success. And if you remember, the expected value of this thing is just 1 divided by P, where P is the probability of the success. So this is just continuation from the last problem. So recall that P is, or was, 0.0625. So our expected value is just 1 divided by 0.0625. So once you do that calculation, 1 divided by 0.0625, we get a total of 16. So we would expect to go through 16 patients until he gets his first successful surgery, if he's not hired first. Another continuation, the probability that in 10 operations, exactly 2 of them are successful. Well, here things have changed slightly. We've got 10, we want exactly 2 of them. I don't specify which ones they are, and furthermore, it should be a big clue that I've got more than 1. If I said exactly 1, then, you might think, well, okay, is that the last one? It might be geometric. If it's any one of them, then it's binomial. But here, exactly 2, then yes, it must be binomial. These things are, of course, still Bernoulli trials. Each patient is a trial, success or failure. We go on to the next one, operate on them, success or failure. I don't know. So we have this binomial. We want to know probability that exactly in 10. So here we've got our total number of trials is 10. And we want x, or k, k or x, I suppose, to be 2. So we want exactly 2 of them. So this probability looks like this. Probability that x equals 2. It's going to be, I'll write it out, n take k times the probability of the success, which is p, to the k, times q to the n minus k. So once we plug all this stuff in, and again, this is just a continuation, so we still have the same P's and Q's here. So we still have this stuff going on, P and Q, and it's different, so it's not 4. It's going to be 10 here. So we got a few things to look at. Let's fill this in. We've got 10, take 2, these kind of vertical parentheses like that. P is 0.0625 raised to the, well, K here is 2, so square it. And Q was 0.9375. Let's go ahead and raise this to the, N was 10, K was 2, so 10 minus 2 gives us 8. And this makes sense. If we're going to get exactly 2 of them successful, we've got 2 successes, and we've got 8 failures. This multiplication, this term on the left side, just deals with the number of ways we can actually have this happen. So first of all, let's go ahead and calculate what is 10 take 2. Once we go through the process, we see that this is 10 factorial all over 10 minus 2 factorial, which is 8 factorial, times 2 factorial. We can do a little bit of cancellation. Remember, this is 10 times 9 times 8 times 7 times 6 times 5 times 4. So we will really have 10 times 9, and then times these 8 factorials. These will cancel on the top and the bottom, and we'll be left with 2 factorial. So we'll have 10 times 9 over 2 factorial. 2 factorial is just 2 times 1, so that's just 2. So I could just go ahead and say, well, this is 90 divided by 2. It's going to be 45. Right? So this is just something that we've done off to the side. So ultimately we've got 45 times, let's go ahead and see what these decimals come out to be. 0.0625, square it. You get the really small number, 0.0039. And then 0.9375 raised to the 8th power, multiplied by itself 8 times. I have to squeeze it in here, sorry. This is all being multiplied together. 0.5967, or roughly right there about. So we multiply these together. So 45 times 0.0039 gives us 0.1755, and then times 0.5967 gives us 0.1047. So the total probability here is going to be 10.47%. Again, we want you to leave it as a decimal, so just 0.1047 is enough. In 40 patients, how many successful surgeries do we expect? So here we're talking about the total number of successful surgeries we have. We're not saying anything else. So we've got this fixed n here. N is 40. That's fixed, right? And we want to know, yeah, the total number. So here we're talking about, because it's just, I don't care which ones they are, just the number of successes, this is binomial. So this is, again, still an expectation. We still want to find the expectation here. However, it is binomial. So if you remember, the expectation for a binomial process is n times p, where p here was, recall, 0.0625. So we would plug these in. 40 times 0.0625 gives us 2.5. So we were asked to go ahead and express this as a decimal to actually input this as 2.5. So it was really a quick problem. So we got 20 questions, 4 questions each, or I'm sorry, 4 choices each, and we want the probability that on this multiple choice test, we guess exactly 5 correct. So first of all, what's the probability of getting just one of these things correct? There are 4 choices, 1 correct answer. So we've got 1 out of 4 or 0.25. So that means our Q is 0.75. So this is just for one of them. And now, again, we have guessing exactly 5 correct of these 20. So N here is 20. And we want exactly 5 correct. So this tells us it's binomial. So K here is 5. Or if you like, you can put X. So similar to the last problem, or I guess problem number 7, is X equals 5. So this is going to be N take K, right? N take K times P to the K times Q to the N minus K. Plugging this in, we get 20 take 5, and we get 0.25 raised to the 5th, and Q is 0.75. And then this is 20 minus 5. So this is 0.75 to the 15th power. So just like before, let's go ahead and do 20 take 5 out to the side. It's 20 factorial. All over 5 factorial times 20 minus 5 gives us 15. 15 factorial. Right? These things always add up to give us that. We can do a little bit of cancellation here. This would be 20 times 19 times 18 times 17 times 16. And then the 15 factorials will cancel. All over 5 times 4 times 3 times 2 times 1. We can take the opportunity to cancel a little bit further. For instance, 5 times 4 is 20. We can cancel those out. And we can see what else. 3 times 2 is 6. So we can cancel that with our 18 to get 3. And so multiplying this all out, we have 19 times 3 times 17 times 16. We do get 15,504. It's a very large number. And that's just for this number of ways to take 5 things from 20 objects. Okay, so putting this all together, we've got 15,504, that's just this, times 0.25 raised to the 5th, times 0.75 raised to the 15th. And you should come out with, let's see, raised to the 5th, times 0.75 raised to the 15th. Should come out with 0.2023 or somewhere thereabout. So this would be the probability of guessing exactly 5 correct. Seems very likely. Or well, not very likely, but not unreasonable. So we got this game. It's played with a deck of 52 cards. So we want, here's the rules. Red card gets you $2, club gets you $1, ace of spades gets you $10. Let's look at the probabilities of these things. We need the value, and we need the probability of each value to find the expected value. So red card, we've got 26 red cards in 52. Or, you divide that out, you get 0.5, right? The probability of getting a club, well, there are 13 clubs out of 52. Or you might go ahead and say, well, you can do it by suits as well. There's two suits that are red, and out of 4, you get half. Or 1 suit out of 4 gives you 1/4. That works fine, too. And then let's go ahead and do the last one. Ace of spades is 1 out of 52, or can't do that one in my head. 0.019. We'll keep it there about there. So the expected value then is just 2 times 0.5 plus 1 times 0.25 plus 10 times 0.019. So it's just, you take each of these values and multiply by their probability. So this is just 2 times 0.5 plus 1 times 0.25 plus 10 times 0.019. And if you do all this out, let's see, we get, well, this should be what? Do it in red here. This should be 1. This should be 0.25. 1 times 0.25. And then times 10 here, we should get 0.19. So if you add all these things up, you should come up with expected value should be 1.44. So our game should cost $1.44. It's not what the question asks, but just to find the expected value. So playing this game, $10 sounds like a really good reward, but we don't get it very often. So this is a good price to play.